A stack is a data structure that follows the last in, first out principle. This means the most recently added element is the first one to be removed. Adding elements to a stack is known as pushing, while removing elements from the stack is called popping. When you push an element onto the stack, you place it on top, making it the new top element. Conversely, when you pop an element from the stack, you remove the element from the top, effectively making the next element in line the new top. Think of it like a stack of plates. You add new plates on top, and you only remove the top plate. Now, let's say you've popped all the elements from the stack and it's empty. If you try to pop another element, you will encounter an error known as a stack underflow error. Conversely, if you attempt to add more elements than the stack's capacity allows, you will encounter a stack overflow error. A stack can be implemented using both arrays and linked lists. We'll first explore the implementation using arrays, and then we'll look at how to implement a stack with linked lists. We'll use Python for the implementation. We'll start by defining a class called stack. In the constructor, we'll set a default limit of 6 for the stack and initialize 3 members: items to store the stack elements, size to track the current number of elements, and limit to set the maximum capacity. After that, we'll define the operations such as push to add elements and pop to remove elements. To define the push operation, we'll start by creating a method called push that takes the element to be added as an input parameter. First, it checks if the stack is full by comparing the current size with the limit. If the stack is full, it will raise a stack overflow error. Otherwise, it will append the new item to the items array and increase the size by 1. To define the pop operation, we'll start by creating a method called pop. First, it checks if the stack is empty by verifying if the current size is 0. If the stack is empty, it will raise a stack underflow error. Otherwise, it will decrease the size by 1 and remove and return the last item from the items array. There's also a peek operation that returns the top element without modifying the stack. We'll start by defining the peek method. First, it checks if the stack is empty. If it is, it raises a stack underflow error. Otherwise, it simply returns the top element without removing it from the stack. Now, let's see these codes in action, along with the visual animation. First, we'll initialize the stack object using the class we defined earlier, leaving the limit set to the default of 6. This stack animation is a visual abstract representation, while the array below represents the actual implementation. After initialization, we'll push elements onto the stack. Pushing means appending elements to the array, which is a constant time operation. Then, the peek operation will simply return the top element of the stack, which corresponds to the last element of the array, also in constant time. Finally, removing an element involves deleting the last element from the array, which is another constant time operation. Next, let's explore the implementation using a linked list. If you're not familiar with how linked lists work, you might want to check out the detailed animated video linked in the description. In the linked list implementation, the top stack element corresponds to the element at the head of the list, while the bottom element is at the tail. Popping an element involves deleting the node from the beginning of the list, and pushing an element means adding a new node at the head of the list. We'll first start by defining the stack class. In the constructor, we'll set a default size of 5, though this is optional. Then, we'll initialize a linked list to store the stack elements, set the maximum size, and keep track of the current size. After that, we'll define all the stack operations, such as push, pop, and peek, to work with this linked list implementation. Let's start with the push function. First, we'll define the function and take the value to be pushed as the input parameter. Then, we'll check if the stack is full. If it is, we'll raise a stack overflow error. Otherwise, we'll insert the data at the head of the linked list and increment the current size by 1. Next, to pop an element, we will first define the pop function. Then, we'll check if the stack is empty. If it is, we'll raise a stack underflow error. Otherwise, we'll decrement the current size by 1 and delete the node from the head of the linked list. The peek operation is also similar. We'll first check if the stack is empty. If it is, we'll raise a stack underflow error. Otherwise, we'll return the data from the head node of the linked list without removing it. Now, we will first initialize an object of the stack class we defined earlier. The stack you see on the right is the abstract representation, while the linked list below, initially set to null, is the actual implementation. Pushing onto the stack corresponds to inserting elements at the head of the list, which is a constant time operation. Popping involves removing the element from the head node, which is also a constant time operation. The peek operation simply retrieves the data from the head node of the list, and this too is a constant time operation. Understanding the linked list data structure is crucial to grasp how this implementation works. We have detailed videos on both linked lists and arrays on this channel, which you can check out for a deeper understanding. Now, let's look at a use case of the stack data structure. Imagine you're editing an image in software. First, you erase something in the image, then you paint something, and then you paint again. These actions are stored on a stack. If you want to undo these changes, the software will simply pop those operations off the stack. This allows you to reverse your actions in the exact order you performed them, demonstrating how stacks are used in real-world applications like undo functionalities in software.